This section is important not so much for the formulas that we derive, but for the logic behind those formulas. One of the big ideas of integration is that you have some quantity that you're trying to find, and you're going to get it by adding up a bunch of really small pieces that approximate the whole thing, and then take the limit as we increase the number of pieces. We see this when thinking about the area under a curve. We approximate the area with rectangles, and then increase the number of rectangles to get better and better approximations. This limiting process becomes an integral, which we can think of as a sum of infinitesimal pieces. It turns out that we could do this with a huge variety of objects. Arc length can be thought of as the distance you travel if you travel along a curve. We will imagine a curve that starts at t equals a and ends at t equals b. The challenge is that the distance formula only gives us the length of straight line paths, so we will approximate the curve with a bunch of straight line segments and then take the limit as we increase the number of segments. We're going to use a differential notation because it's more intuitive than the full formulas as written in the book. Let's imagine taking a close look at just one of these straight line segments. Even though in the initial sketch it's in 2 dimensions, we're going to think of it as being in 3 dimensions. So if we plot the endpoints of this particular line segment, it fits inside a box with sides that we'll label dx, dy, and dz. By applying the distance formula, we know the length of this segment, which we'll call dl, is equal to the square root of dx squared plus dy squared plus dz squared. You should think of dl as a little bit of length. Then the total arc length is the sum of these lengths. If we look at the right side of the equation, we don't have a variable of integration. We also need to convert the differential terms into derivatives. Fortunately, the parameter t saves us on both counts. We can factor out a dt from under the square root, which leaves us with derivative terms underneath and a dt on the outside. And this is the arc length formula. Notice that the square root part is actually just the length of the derivative vector. This gives us a more compact formula for arc length. The limits of the integral are the values of t that mark the starting point and the ending point of the curve. One of the challenges that we've seen with parameterizations is that there are multiple parameterizations of every curve. We can change where we put the 0, and we can traverse the path at any speed we want. This flexibility makes it difficult because there's no standardization for how we view the curve. The arc length parameter changes all of that. Rather than using an arbitrary value to parameterize a curve, we're going to use the physical distance. Once we establish the location of 0, then all the points are measured by their distance along that path. You can imagine taking a piece of inelastic string that we label with distances, and then lining up the string along the curve. The markings on the string correspond to the values of the arc length parameter along the curve. We can also follow this backwards to get negative values. Another way to think about this is that these points are mile markers along the side of a highway. Every unit distance, the marker goes up by 1. To get the arc length parameter, we have to define the arc length function. Let's say we have a parameterized curve r of t defined on the interval from a to b. The arc length function s of t is defined to be the length of the curve from a to t, where t is some point in the interval from a to b. Since we have the arc length formula, we can just write that down. The variable s is called the arc length parameter. Notice that we're using the variable w because the variables s and t have already been used up. S is the arc length parameter, and t is the upper limit of the integral. That's how things go sometimes. We just need to make sure that we're not using a symbol that has already been used for something else. As long as t travels the path without ever stopping or going backwards, we will get a function that's invertible. If we're able to invert this function, then we would get t as a function of s, which we can then substitute to get the curve parameterized by the arc length parameter. Those last steps are often confusing in the abstract, so we will outline a computational process and do a quick example. The goal is to parameterize a curve by its arc length given some parameterization using a generic variable t. The first step is to calculate the arc length function. This will give you an equation of the form s equals something in terms of t. The next step is to solve for t from this function so that you end up with the equation of the form t equals something in terms of s. The last step is to just plug this into the original formulas so that your curve is parameterized with the variable s. These are the steps that we're going to follow in the upcoming example. Let's take a look at the curve r of t is equal to 5 cosine t, 5 sine t, where t runs from 0 to 2 pi. You should be able to immediately recognize this as a circle of radius 5, but even if you don't, you should be able to do the calculation anyway. We simply plug this into the equation for the arc length function. Notice that even though this is a two-dimensional vector, the ideas still apply. We won't talk through the details of this integration because this is an integral that you should have seen many times by now, and you should be able to recognize the trick of using the Pythagorean identity to simplify the radical term. This gives us the equation s equals 5t. The next step is to solve for t. It's easy in this example, but this can often be a very challenging step. And then we substitute this in for the t that's in the original vector equation, making sure that we also adjust the interval. And this gives us the curve parameterized by the arc length parameter. You may have noticed that the arc length parameter makes the equation look a bit messier. On the plus side, the arc length parameter has the property that the derivative of the position vector is always a vector of length 1. This corresponds to the idea that you're traveling at a constant speed of 1 unit of distance per unit time. The book also works through a more complicated example in which you have to work a little bit harder to get the inverse. You should take the time to work through that one on your own. In the next video, we're going to talk about the geometric concept of curvature.